Hello again, guys. Today we'll be continuing the topic of the free vibrations, and today we'll take into account the damping inside the harmonic oscillator. Okay, it means that today it will be about damped free vibration of single degree of freedom systems. Okay, and last time we were considering such a case, I mean the sprung mass with the constant spring coefficient K. This time we will take into account the damping and we will get such a thing. Okay, we remember that using the Lagrangian mechanics we are able to find governing equations, and because it's from my previous videos, I don't do it again, that thing. I will write down only the result, I mean the final form of the Lagrange equation, I mean the governing equation, and it will be K over X. Here we have those two another steps which are connected with the looking for Lagrangian of the system and some derivatives. I will denote that thing in that way. Okay, and here we have the result of that computation. You can check it on our previous videos, and we remember that it will be the inertia force due to the time changes of the generalized pendulum momentum, and here we have that contribution of the restoring force. Okay, that thing, it's here. Okay, and last time it was equals 0, but if we have the damper, we know that it's possible to take into account that thing by the generalized forces. And also, again, also last time we stated that the Q can be expressed by the partial derivative of the dissipative potential respected with the x dot, where the x is our generalized velocity. Okay, and if we want to find that Q for our case, we have to find the value of D. And again, for D, it's really simple to find that formula because it will be 1 over 2 times C times relative velocity of the damper, I mean the relative velocity of the both ends of the damper, square. Okay, in our case it's really simple to compute because like we did that in the material connected to the Lagrangian mechanics, we can compute it as a time derivative of the deflection. It means in our case, in that simple case, it will be exactly x dot. It means that if we want to compute that extra force, we have to take the minus partial derivative respected with the x dot of the 1 over 2c x dot square. And as a result, we see it's a minus cx dot. Okay, and now we are able to include that fact. It means that I will rewrite that equation. I mean, here we have the x mass times x double dot plus kx minus cx dot. What we have as a result? It will be mx double dot plus cx dot plus kx equal to 0. It is our governing equation of damped free vibration. Okay, now we have to solve it. Like last time, classification of that equation. It is second order homogeneous differential equation with the constant factors. Okay, how to compute that equation? First thing, we have to make the highest derivative free. I mean, we have to divide it by the factor of the x double dot. As a result, we have x double dot plus c over mx dot plus k over mx equals 0. Here we have such a governing equation in the form of the accelerations. And the next step, typically, like in literature, we are introducing some extra symbols, which will be convenient for further computations. And C over M, it will be 2h. Y2, you will see in the moment. And the next step, like last time, like in the case of the undamped vibration, we have the omega 0 square. Okay, and if we put that numbers, we have the x double dot plus 2h x dot plus omega 0 square x equals 0. Okay, it is our equation which we have to solve. And like last time, we are using the Laplace method. I mean, we are predicting the solution as a product of the constant connected with the initial condition S and exponent of RT. Okay, like always, it is predicted solution. It means that if I put it into equation, if it is the solution, it has to fulfill that equation. It means I have to put it here. For that, we are computing first and second derivative of the assumed, of the predicted process. I mean, the first derivative is as follows. I mean, CR times ERT, and second derivative, it will be C times R squared times E to the RT. Okay, we have the three derivatives. We are able to put everything into our governing equation. As a result, here we have CR squared ER to the RT plus 2H CR A RT plus omega 0 squared C ERT equals 0 because it's a homogeneous equation. And now we see that we have the common factor in the form C ERT. It means I will put it here, C times exponent of RT, and against to the C exponent RT, we have 2HR plus omega 0 square. Okay, and here we see that like last time, like in the previous video, we see that here we have that C exponent RT as a component, as a term connected with the predicted solution, and something which is called characteristic polynomial. I mean, some description of the physical parameters of the physical dynamic answer of the system, and that we see it depends only of the system properties. Okay, how to solve it? We see that that thing cannot be 0, the same as we are talking about the C. C cannot be 0. It means that if you want to find the condition where the entire product will be 0, we have to looking for the roots of that characteristic polynomial. I mean, 2r squared plus 2h r times omega 0 square equals 0. Okay, and we see simple parabolic equations, two roots r1, 2 in the form minus b plus minus square root of b square minus 4ac over a, which are over 2a, sorry, which are factors of the subsequent orders of that polynomial. Okay, and we remember that from the theory of the parabolic equations that a will be factor of the r square, b it will be factor of the r, and c it's a factor of the r0, I mean the free term. Let's write it down. I mean a is 1 in our case, b is 2h, and c it will be omega 0 square. Okay, what can we do next? We have to put the values here. Okay, it means that we have 2 times h plus minus square root 4h square minus 4 omega 0 square over 2. And we are able to find the common factor here. I mean, here we have 2 minus h, maybe I will improve myself because it doesn't look especially good, minus h plus minus square root of the h square minus omega 0 square over 2, we have to close the parentheses. Okay, and by simple simplification, we see that we have minus h plus minus square root of the h square minus omega 0 square. Okay, it means our both roots, I will rewrite it again, are given by some real number minus h, I mean something connected to the damping, and plus minus h square minus omega 0 square. Final solution, I mean the final integral of our differential equation, will be given by the c times exponent of r1t plus, sorry, c1 of course, plus c2 exponent of r2t. If we put the numbers, we will see that we have c1 exponent of minus h plus h square minus omega square times t plus c2 exponent of minus h minus square root of the h square minus omega 0 square times t. Okay, it is the final form of the solution, of the homogeneous part of our equation. Let's make some discussion. We can consider three cases. First case, where the h square is bigger than omega square. Okay, then here we have two real numbers, two real negative numbers, okay? Because if the h square is bigger than omega square, we see that h square minus omega square, it will be something which will be bigger than 0. Second thing, h square minus omega 0 square square root will be smaller than h. It's obvious because if I take even omega 0 square as 0, then h square square root, it will be exactly 8. It means that for any value of the omega 0 square, the square root of that difference has to be smaller than h. It means in that case and in that case we have two negative numbers. It means the solution of that case, it will be linear combination of two exponents. We remember that the exponential function looks like, I will make some auxiliary graph, looks like that. That function, the negative exponent cross 0 at the cross y-axis in the point 1. It means, in our case, for the time 0, we have c1 plus c2 due to that equation, because that thing will be 1, that thing will be 1, and it has to cross that line somewhere here. Okay, it is the result of that computations for the first condition. Okay, second condition, h square is equal to omega square. It means that that square root and that square root will be exactly the same. Then, due to theory of the differential equations, the solution will be a little bit different. It's connected with the mid of the linear independently of the particular solution. It means that it will be CA minus HT, and of course the second part will be exactly the same. But it isn't possible, that is why we will put the T here. And the graph of the process will be as follows. That function looks like my negative exponent function. Okay, it means it will look like that. I will put it as a dashed line here. Okay, here we have C1. That function at the beginning, where the beginning of the process is where the t is more important, then the function will look similar to the linear function. And then where the exponential function is most important, then it will look like exponential function. Again, the entire process, I mean the total process, looks like, oh, maybe not, it's not good color. the total process will look like that. Okay? And the last case, where the omega 0 square is bigger than the h square, then h square minus omega 0 square will be, it will be element from the complex, let's say, because h square minus omega 0 square will be smaller than 0. And then we are able to change the form for the r from the complex number. We are able to change the form of RT to the form of the linear combination of the cosine RT and sine RT. And as a solution, we are getting that it will be exponent of minus ht times d1, different constants of the integration, times sine omega 0 square minus h square square root t plus d2 times cosine square root of the omega 0 square minus h square times t. Okay, let's close the parentheses, and it is that process. We see that it's some kind combination of the vibrations and exponent modulation. Okay, it will look like that. I mean that oscillation due to that thing are here, and it's modulated by the negative exponential function. That process is given by minus ht. Okay, guys, thank you for your attention. We did some discussion of the free vibrations of the damped system. As you see, it isn't especially complicated. See you, good luck with that stuff. See you next time.